Whew, all the things. All right, y'all. So, ooh, that's way too loud. Okay, so first, joke of the day. While I wait for that, I click the thing open. I looked up the definition of opaque. It was not very clear. Because it's the definition of what opaque means. That's good. All right. Couple logistic points for you all. So, beginning of the week, always fun and exciting things. First one. So I sent an announcement. The student perception of instructor is open. You get absolutely nothing out of completing that. But I say that for full transparency. Student perception of instructor, there's no bonus points, anything like that. I mean, I think you have to do it to get to my UCF or whatever. So I say that with full transparency, but I would personally appreciate it if you all filled that out for me. And I put that in the announcement, everything on the sample announcement. That is one of the best ways for me to get feedback from you all. So as a teacher, like anything in life, should be trying to improve. You all are the ones I'm ultimately trying to serve. Yeah, UCF pays me, but really the reality is you all pay and then the money kind of comes to me. Some small amount of it. But you are the ones I am seeking to serve. You're the reason I do this job as people. I'm in teaching not for UCF, not for Lake Mary High School, but to support you all. So I really do want to hear from you all, what your thoughts are and stuff like that. At this time, I get no benefit if you rank me high, I get no detriment if you rank me low. So it's not again like I'm getting anything necessarily out of it, other than what I'm getting is feedback and trying to improve to be a better teacher. I want to hear from you all. I want your brutal, honest opinions on it. So, a lot of it is just like strongly agree, strongly disagree. All of that is great. At the bottom as well, though, there's those pre-responses. I read through every single one of those because I want to hear from you all what was good, what was bad. That's kind of like a survey for me of, hey, what can I do to do a better job? You can always improve, y'all. You will never be perfect. I will never be perfect. So, I want to hear from you all what works and what doesn't. What parts did you like? What parts didn't you like? What parts is there any suggestions you have? All of that is immensely useful. Please, please, please fill that out for me. If not, I'll never know if you fill it out. I'll never know if you don't fill it out. It's all anonymous. So again, there's no record, there's nothing so again, it's just, that's my plea to you all though. Do it so I can be better. I would very much appreciate that. Love hearing back, love reading through those and kind of, again, figuring out the next year, because I hope to keep doing this stuff. So that's one announcement. Second one is the free response grading is going very smoothly. He just sent me an email today saying so there's multiple versions. He's two-thirds done. He's two-thirds done with the grading after about a week's time. That's pretty good. So that means he's on track to finishing this week, which reaches that 2-week kind of goal that I originally set for test 1. So it seems like he's achieving that for test 2, which is awesome. Once I have those, also he said people are doing well. He said the averages are very high for this one. So that's also great to hear. Once I have those, depending on when I get them. If I get them on the weekend, who knows whether I'll see it then. But once I see that I have them, I will do my best to get those out to you all in 24 hours or so. There's a little bit of, I have to look at them, look at the averages, see if I'm going to curve them, all that jazz, finagle things around. So it's not just immediate receive them, upload them, done. I do have to spend a little bit of time on that. Yeah.
This is kind of like an unrelated question.
Sure.
Are you teaching 2049 this year?
Yeah, I've gotten that question a few times, which I very much appreciate. I have no idea. I have absolutely I know zero idea if if anything of what I'm teaching in the fall. As soon as I find out, because I've had that people ask that question, if I'm offered a choice of any sort or have any say in it, I'll try to teach 2049. And if that somehow magically I can have that conversation before the end of the semester, I'll send out an announcement. Otherwise, I have no idea how I communicate that to you all. Do you all have any ideas? After the class ends, if I send out an announcement, do you all see it? No? Okay, yeah, so I have no idea how I'd send out something. I'll think that through.
YouTube channel.
Oh, yeah, there we go. Okay, great. If I somehow, some way figure out what I'm teaching, yeah, that's great. YouTube channel will work. I can't think of it. But yeah, sadly, I have zero idea. If I had any inkling of anything, because I even got questions like, if you were teaching it, would it be at this time or that? No idea. Zero clue. But thank you, I appreciate that. Let's see, I think there was a third announcement. Last week, final. The one question. So remember I told you there was a question that not everyone, that less than 50% of people got right. So what question was that? It was, I gave a function for a wave that was, it was something like this. 6 cosine of 6t, and I said, what is the frequency? What is the frequency? Not what is the angular frequency. What is the frequency? And this is where you had to remember that the form of this equation is amplitude times cosine of omega t. So omega is angular frequency, angular velocity, same thing. So in this case, I asked for frequency. Frequency, you need to take the angular frequency and divide it by 2 pi. Conversely, if you want angular frequency, you multiply f by 2 pi. So, there you go, y'all. That was the one. That was the only one that majority of people missed. And as I've kind of already told you all, you can guarantee there'll be a question like that in the final. Because at the end of the day, if I ask a question, my goal is that it was supposed to be assessing something that I thought was meaningful. You all been updated on what that is, so hopefully this one will do well in the final. That is the only question I'll give you kind of hints and tidbits on. Working on the final, I think I have a good draft of it at this point. I'm going to go through it. So the way I design any test, I make a draft of it, so I go through, make a bunch of questions. I then go through all those questions, so I solved them all originally. I go through it second time, and I time myself for how long it takes for me to solve them, with, not just rushing through it. I then multiply that by like 4 or something like that, 4 or 5, and that gives me how long I kind of want to give you all to solve it. And then I also evaluate it based on difficulty and like whether it's going to be too much or stuff like that. So again, first draft is almost done. My goal is to get it to like 45-ish questions. Currently it's at 47. Maybe it'll stay at 47. Maybe it'll drop down to 45. Probably won't drop below 45. Remember, my goal for this test is that if you know what you're doing, you can finish it under 2 hours. The average individual will be able to solve it and finish it under 2 hours. I say that again, I know everyone's different. Some people take longer on tests, that's fine. That's perfectly fine. If it takes you longer, but you still get a great grade, awesome. Like, time is not something I'm assessing. So I mentioned that 2-hour mark purely as a reference. You all get 2 hours and 50 minutes. I'm not designing a test for 2 hours and 50 minutes. I'm not trying to design a marathon. It's going to be 45-ish questions. Like, it is going to be a lot. So my goal is to get depth and breadth, meaning depth meaning appropriate difficulty level for what I need you all to know. Breadth meaning I'm covering the range of things that we've covered. But I'm also trying to balance that with time. I recognize there is such thing as mental fatigue, and so I'm doing my best to keep that reasonable and not make it so that by the time you've gotten to 30 questions, your brain is pudding and no longer working at the level it should be. There is something to be said. You all will have jobs one day where you're doing a lot of this stuff all the time, but the reality is you get breaks. Sure, there is something to be said about being able to use your brain for extended periods of time, but at the same time, I don't want that to be too much of a barrier. So, working on it. I'm going to do my check this week and then send them out to the printing press, hopefully by next week, and it'll be great. Remember, just multiple choice questions. The ceiling of the difficulty is a little bit higher than the multiple choice on previous tests to make up for there being no free response. So the free response was kind of your all's difficult section of the test, the most involved. So I'm just kind of, since that's gone, raise it up. Anyway. Okay, I've kind of mentioned the test stuff. That's probably the last I'll mention it. But remember, you all get a sheet of paper front and back as well. Just keep reminding you of that. Bring your own paper. You can't share it with someone else. All that jazz. Any questions, comments, concerns before we get into our last PowerPoint slide? This is the last one, y'all. How exciting. All right, so we're going to jump into it. Moment of inertia and angular momentum. I'm going to leave this weird writing on the front. Probably confuse people, but whatever. Moment of inertia and angular momentum. So we've talked about rotation. And I continue to remind you all that the rotational variables pretty much all have a linear equivalence, which is a fancy way of saying angle goes with theta. Or sorry, x goes with theta. Velocity goes with angular velocity. Angular acceleration goes with acceleration. So we're going to introduce it. We have regular momentum. We're going to have angular momentum. We had regular kinetic energy. We're going to have rotational kinetic energy. We had F equals ma. We're going to have torque equals I alpha. So we're going to build some more of those. Yeah.
What is this stuff related to like RPMs?
So RPMs would be,
Angular frequency.
it'd be a frequency, revolutions per minute. So frequency is how often something occurs every second is the base unit. So RPMs would be like a conversion for regular frequency. Revolutions per minute, regular frequency is like revolutions per second. Yeah, so seconds, minutes, so they vary a little bit there. But yeah, frequency to RPM would be normal frequency. Yeah, it's a good question. Whereas angular frequency is all about radians per second, angles per second. Yeah. A lot of this PowerPoint is going to be about moment of inertia. Moment of inertia is a very fancy word which basically just says how is your mass distributed. We have not cared how our mass is distributed kind of up to this point. Remember our free body diagrams all looked like blocks or circles. When we drew our pictures, we didn't care what the thing was. A person was the same as a box, was the same as a rocket. We haven't cared about shape. We have to care about shape for things spinning. So moment of inertia is going to kind of be like mass. For rotation, mass is what we use when we were talking about things moving in straight lines. Moment of inertia is what we're going to use. It's going to involve mass, but we have to care about how it's distributed. We'll figure out why today and the rest of this week. We may or may not finish this PowerPoint this week. Worst comes to worst, it boils into Monday. We still have Wednesday, Friday, another Monday after that for review. So we're chill at this point, y'all. We got plenty of time. We're not in a rush. So yeah, we're going to talk about what moment of inertia is and how to calculate it. We're going to talk about Newton's second law. So that's F equals ma. Well, there's a version of that for rotation. That's torque equals I alpha. We have to figure out alpha. We'll define angular momentum and do conservation of momentum. We'll also, I forgot to put this sheet, rotational kinetic energy will also get in here. So all the linear things, we'll have all the rotational things. It'll be great. Okay. I did not expect you to know the answer to this, so take a guess. I roll 4 objects down a ramp: a sphere, a hollow cylinder, a solid cylinder, and a hoop. If they all have the same radius and the same mass, I need to clarify that here. If they all have the same radius and the same mass, and are released from the same height, which will reach the ground first? I really want to point out, there's not an answer that says at the same time. Meaning, one of these will reach the bottom first. Take a guess. Take a guess. I have not taught you this. Which one do you think will reach the bottom first? It will be one of these. Ideally, I'd have a demo kind of showing this, but I haven't been very good at reaching out to the demo people and asking for things. But you can prove this to yourself if you actually have these objects, same mass, same radius. I don't know why you would. I have no idea why you would have 4 objects with the same mass, same radius, and all these different things. But if you did, there's plenty of experiments to prove this, so I'm not making this up. All right, we'll go to 50 seconds. This is literally take a guess. There is no math at this point to figure this out. I have not taught you any of the math, and even if I did, oh gosh, it would take you so long to do the math to figure it out. You'll see why. All right, 5, 4, 3, 2, 1. Okay. The answer is a sphere. And I'm immediately going to knock out the reason that most people think it's a sphere. Most people think it's a sphere because it has a single point of contact. That's not the reason. It does not have to do with how much is contacting this. The amount of contact for something rolling doesn't matter unless that object is slipping. That's the only time where friction plays into things. So like bearings are spheres, and they are, so bearings, I'm going to draw a picture of this and immediately erase it because it has nothing to do with the answer here. But you all are going to experience bearings. So a ball bearing is a convenient way to make something spin really simply. And it's this. If you want the outside to spin, you put some spheres to the point of contact slow. That only matters for slipping. We are not going to consider slipping at all. Slipping does not matter in our problems. We're going to assume no slipping. So I only mention that to say slipping, no, not that. Yeah. That's a great question. So slipping, when something rolls, in an ideal world, it rolls, and if it rolls one full revolution, it moves 2 pi r distance. It moves the full distance. Slipping means that it slips in place, meaning when it's rolling, it can slip and not actually make any forward movement. Easy way to think about this, imagine a tire spinning on ice. There's a lot of slipping there. The tire is spinning and it's not resulting in the car moving forward. Sometimes you want slipping, sometimes you don't. Engineering is all about taking advantage of all the way the world's work. And anyway, sometimes advantage, sometimes not. All right, has nothing to do with the answer to this problem, but I do mention that just because that's immediately people's thought. Single point of contact. It's not that. We're going to learn today all has to do with how the mass is distributed. How is the mass distributed with respect to the rotation, where it's rotating? So we have a rotational axis. Rotational axis is the point at which it kind of circles through. And the rule is it's easier for things to spin the closer the mass is to that spot. The closer the mass is to this axis of rotation, so there's my axis of rotation, the closer it is, the better it is. So the ideal thing for rolling, the thing that would reach the bottom the quickest, is like an infinitely thin rod that's right along that axis where all the mass is right on that axis. That's the ideal. Spins super easy. The farther away it is, the more it's got to kind of move the same distance. The farther away it is, the more we'll see some derivations why, the worse it is. So, a hollow cylinder, the mass is far away. So a hollow cylinder, if we kind of draw that example, the mass is really far away. In fact, it's all kind of as far away as it can be. That will not rotate easily because the mass is all far away. A hoop is the same thing, just without a length to it. Same thing. A hoop will not rotate as easily. A solid cylinder is better. A solid cylinder is better because some of the mass is close to that axis of rotation. But a sphere is best, in this case, out of these options. And this is a little tricky to draw, so I don't even know if I'm going to try to draw it. A sphere is best because compared to a cylinder, if you compare, I'll let you all kind of visualize this on your own. A sphere, more of it is closer to the cylinder, and you can it's really tricky to draw. I'm not really sure the best way to draw it, to be honest. But a sphere, more of the mass is closer. Yeah.
So I was thinking the sphere was hollow.
Oh, yeah, that'd be bad. Hollow sphere would be bad.
That's what I'm saying.
Yeah, so let me actually add that for future generations. If the sphere was hollow, it'd actually be bad.
Would it?
Because the mass would be farther away.
So how would that compare to the hoop?
Hoop would be worse because all of it's far away.
But wouldn't a hollow sphere?
Hollow sphere, some of it's close by, specifically like on the sides of it. On the sides of it, it's close by. Yeah.
So in order would be A, C, B, D.
Yeah, that's a good question. What would be the order? The order would be, let's rank them from best to worst. To one is best. And I say best to worst. Let's actually change the wording here. Fastest, slowest, maybe? That's even not the best. Let's just say best to worst. I say best to worst is not great terminology because sometimes in life you don't want things to rotate super quickly. It all depends on your application. That's a very important thing for you all to realize as engineers, if that's or computer science or anything in life. What is good sometimes will be bad other times. It all depends on your application, and that's a very important question. Sometimes you will want a metal that bends really easy. Sometimes you want a metal that's really stiff. You have to decide what the application is, and that's a lot of what engineering is learning all this stuff to make the best decision possible for the application. Very important consideration. So again, best to worst, not ideal. So 1, 2, 3, 4. Sphere will reach the bottom of the first. And then after that, the solid cylinder will do the best. The hoop and the hollow cylinder may actually be tied. I will be able to answer that question more in detail when I introduce it. So this all has to do with how the mass is distributed. That's moment of inertia. Moment of inertia gives us a value, and we'll see some equations with that today. But this is kind of a little preview. This is why this stuff matters. It's not as trivial as you all think. So, all right, there it is, the words I've been saying. The farther mass is, the harder it is to rotate. Why? We can actually go back to a previous word we talked about, momentum. Remember, momentum is kind of how hard it is to stop something / move something. That was my hand-wavy definition of the word. Momentum was that. If you just replace velocity with the rotational velocity... Ooh, what the heck is this? Theta, that's not right. Should be that times omega. Time to find the Greek letter omega. Fingers crossed. Oh, no. Ugh, hate finding Greek letters. Did I do good? Nope. All right, I'm not going to bother. I'm just going to put it in here. I'm not going to waste your time. We'll put a W. I hate it, but it's going to do the job. Boom. The farther away you are, the more force you kind of need to make that happen. Yeah.
So by center, you mean axis of rotation?
Yeah, the farther it is from the, let's put that here, axis of rotation. That's very important because the center isn't always the axis of rotation. You can rotate anything about any axis you pick. There's no rules to this. It, again, all depends on how you apply it. Yeah, so you're going to need more force because the farther your radius are, harder to get that high momentum. What about torque? Yes, if you have a greater radius, we talk about force, yes. But remember, y'all, door, if you push the outside of the door, it doesn't rotate super quickly. While, yes, it is harder to kind of push a door near the center of it, the reality is it will swing really quick. So, all right, so how do we characterize this? This next slide is going to be a whole bunch of math that's just kind of building us to it. Let me go and show you. We are going to have a nice slide that summarizes everything. We'll get to this, but I'm going to derive this first, so just know it'll be nice and organized. Okay, so kinetic energy. Kinetic energy is 1/2 mv squared. That should look super familiar. Then we replace velocity with omega r. Remember, you want to go from translational to rotational, multiply stuff by r. So we get this new equation, 1/2 mr squared, omega squared. Omega is at W, angular frequency. All right, great. Now we have the rotational kinetic energy. So the problem is, let's just look at a cylinder. When you're looking at a cylinder, and that cylinder is rotating down something, the radius changes. If I take this little spot right here, it's got a radius. If I take this little spot right here, it's got a radius. If I take this little spot right here, it's got a radius. So fun fact, if you ever want to add up a bunch of small contributions, integral. That's why we have an integral down here. Well, we will. It's not here yet. We'll see. For now, it's a summation, but we don't use summation signs because that's how you add an infinite sum of things. That's all an integral is an infinite sum of things. So, we see this down here, recognizing, hey, the mass, the radius changes for each little tiny piece of mass. And again, we get this nice little term right here, woohoo. This is the slide that's really helpful. So here's that I. There's that I, that's the moment of inertia, that's a symbol for it. It's a very inconvenient letter to write. I, you may think, why? If I use the normal font I use, it looks like an L, which is not ideal. So capital I, really make it clear it's not an L, it's a capital I. A measure of the resistance of a body to change its rotational motion. What a bunch of jargon. The higher the moment of inertia, the harder it is to spin something. There you go. The equation for it, there's two of them. A summation. There is a couple cases where that summation will come in. Those are very specific circumstances. Those are the easiest ones to solve. We'll see like one or two of those. The reality is, how do you find the moment of inertia of different objects? You integrate. We will have a couple practice problems where I have you doing integrals. They're very specific problems. I cannot actually have you calculate the moment of inertia for a sphere, because a sphere is a three-dimensional body, meaning you need a triple integral. You have to learn triple integrals, you're spinning. So, a lot of these moment of inertias, they're different for every object depending on the shape of the object, how the mass is distributed, and what the rotational axis is. Fun fact, I'm going to give you most of the moment of inertia for objects, so you spin. Yeah?
So to maximize spin, you want all the mass in the middle of where the axis is.
If you want to make something spin really simply, have it as close to the axis of rotation as possible.
Or as far away as possible.
If you want to have a large torque, you want to push something as far away as possible. Yeah. So a good way to think about this then, to kind of remove some of that, this applies in space. This applies in space. So if you have an object in space, even though there's no gravity, it is harder to spin something where the mass is really far away, and it's easier to spin something when the mass is really close. We're not talking about how we're making it spin. If you want to get it spinning, you should push it far away. So that's a whole different story. If you want to get it spinning, where do you apply that force? That's a different story. But if you have something, how easy or hard it is to get that object to spin does depend upon how the mass is distributed. Yeah?
So it's not just like the wheels, the gears that have like teeth and stuff, and then you change it, say when one spins really fast, and then you switch it into one.
So gear reduction is more of a torque kind of thing. If you have a big gear spinning quickly, and I make it into a small gear, that small gear will spin insanely quick kind of thing. So it's a little different. An analogy for this is, if you want to store a lot of energy, you want something that the mass is distributed far. So like a flywheel. A flywheel will have the mass kind of distributed far because it stores more energy. I guess that's one application of this. As usual, the way to understand this rotational stuff is what is the linear equivalent. So what is the linear equivalent to moment of inertia? So let's just think through the wording here. Moment of inertia is a quality of an object that makes it hard to spin faster or spin slower. The quality of an object that makes it hard to accelerate angularly. The quality of an object that makes it hard to increase its angular acceleration. What is the quality of an object that makes it hard to accelerate normally, linearly? What quality of an object, if I push it, makes it really, in space, remove gravity. What quality of an object, if I try to push something in space, what stuff's hard to move?
Inertia.
Inertia, and what affects something's inertia? What's the main variable? Mass. This is like mass rotation. The higher your moment of inertia, the harder it is to spin it faster or slow it down. Just like the bigger the mass, the harder it is to push it, to increase its regular acceleration. So, this is like mass. And you're like, but it has mass in it. Yes. But conceptually, if you understand how mass affects something's acceleration, you can understand how moment of inertia affects its angular acceleration. All right, a lot of words because right now the beginning of every lesson is always very conceptual, introducing the ideas, and then we introduce the math. If you understand the concepts, the math is easier. If you can do the math, they don't always go both ways. Okay, so this is the easy case. This is the easy case for calculating moment of inertia, and I'll actually kind of so I'm going to open it up, and I'll kind of walk you all through it as you're solving it, because I haven't taught you this, and it may be a bit of a leap. A 5 kilogram ball, we're going to assume this ball is infinitely small. That matters. A 5 kilogram ball is attached to the end of a 2 meter string. We're going to assume the string has no mass. Lots of assumptions here, but very important assumptions. If we spin this ball in a circle, what is the moment of inertia of the system? Look at that. The assumptions are at the end. I should have just kept reading. Assume the string is massless and the ball is a point. So, here's my axis of rotation. here's my string. I'm going to make it dotted to kind of insinuate that it's like it's there, but it has no mass. And here's my ball. A point. Here's my 2 meters. Here's my 5 kilograms. And I'm going to remind you all that the moment of inertia is the sum of all the objects, however many objects you have, take their mass, multiply it by their distance away from the rotation squared, add them all up. If I had 5 objects, I would do it 5 times and add them all up. I only have 1 object here, y'all. This is kind of the simple case of moment of inertia. One single point located a set distance away with a set mass. And all that mass is right at that spot. We're doing great, everyone. Again, this is kind of the simplest case of just like a single point. We'll go to like 2:0. No, we'll go to 2. The math here is pretty simple. We'll close it out in 5, 4, 3, 2, 2, 2, 2, 2, 2, 2, 1. Did it work? All right, 1. Great. 0. All right, so again, this equation says figure out all your masses, figure out how far away they are, multiply those. If you got another one, and then add it, add. So if I had one object, I would do the mass of that object times how far away it is squared. If I had a second one, it'd be the second mass and how far away it was, blah, 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 blah. However many you have. Well, we only have 1. We only have 1. So in this case, I is just going to be the mass of this object, 5, times the radius, how far away it is, 2 squared. So that's 5 times 4. I will risk not using a calculator. And the units, y'all, come from the math. What's the unit for mass? Kilograms. What's the unit for distance? Meters. The meters get squared. So the units here, just like the units for like momentum and all that kind of stuff, they just come from the math. So, boom. Good job. I think we all pretty much got that. Awesome. So now you can imagine, I'm not going to ask this question like as a clicker question. You can imagine if there was a second object here, which maybe had a mass of 3 kilograms, and instead was 1 meter away. If I had that, then I would do 3, I would add that to it. And every single mass that you had, you'd keep adding, however many you had. So if I want to find the moment of inertia of a sphere, I find how much that one, that dot contributes, then that one, and that one, and that one, add. That's an integral. Yeah.
So if the string had mass.
If the string had mass, we'd have to do an integral.
Yeah. Okay.
You would have to do an integral. You can't like do center of mass or anything like that, as tempting as it is, because the string, the part of the string that's closer will be simpler. And that is the only case that we're going to end up solving together, is a one-dimensional rod that's spinning.
Okay. Well, because I thought maybe you could do like an infinite series or something.
Do what? Infinite string?
Yeah. Or like infinite number of points.
Yeah, which is an integral. Yep. An integral just basically breaks into small pieces and does them all. So we will do a string, i.e. a very thin rod. A thin rod and a string are the same thing. Assuming that string doesn't wiggle. If it wiggles, oh, disaster. Oh my gosh. So, like, all the bodies that you calculate moment of inertia for, we're going to assume rigid bodies, because if that body deforms, it's got a new moment of inertia now. You can imagine how complex this gets in the real world. As things deform, their moment of inertia changes, which changes how they behave. Rotational stuff, y'all can get. This is what makes rotational stuff a little tricky. At least for non-rigid bodies. The reality is, okay, let me just show you all this slide. Here's the moment of inertia of a bunch of objects. Bam, just done. And this is how some of the problems are going to look like for you all. I am not going to have you find the moment of inertia of 3-dimensional bodies. The most I can have you find the moment of inertia is 1-dimensional. If it's a 2-dimensional body, you need a double integral. You haven't learned those. You want to do a 3-dimensional body, you need a triple integral. You haven't learned those. So 1-dimensional body, which is going to be this rod, this axis, that one we can actually derive together. Yay. The rest of them, once you learn triple integrals and stuff like that, you can do them. But notice, what I want to point out here is to go back to our first clicker question. Let's highlight the things that showed up in our first clicker question. We had a solid sphere. There's a solid sphere. There is a hoop, and it's very important. Notice, I have a hoop here, and I have a hoop here. The moment of inertia changes based on where it's rotating. So this one is rotating like a coin. That one's rotating like a coin. The one up here is rotating like a hula hoop rolling down a hill. Depending on where it's rotating affects how the mass is distributed, which affects the moment of inertia, which affects everything. You can see how this gets messy real quick. All right, so great. What I want to point out, though, is we got our sphere, we have our hoop, we have our solid cylinder, and we have our... Okay, so this one is a cylinder with some thickness to it. And you can see all the different moment of inertia, and if we just rank them, notice they're all mr squared. Every single one of these equations is basically mr squared with a number in front. And the question is, what is that number? Every single one of them boils down to that. The smaller the number, the easier it is to spin.
Are these just different Regan sums?
Regan sums. No, it shouldn't be a Regan sum. I have to think what a Regan sum is. But because I wouldn't think of using a Regan sum for this, I'm going to say no.
Well, a Regan sum is just an integral, though, isn't it?
Is it a specific integral? It's been a hot minute since I've had to do Regan sum.
It's just defining like the infinite area under a curve, isn't it?
Yeah, the Regan sum.
Oh, yeah, okay. Yeah, an integral is just a Riemann sum. Yeah, they're the same
So,
thing.
like, these are just different types. Okay, never mind.
They're integrating different ways, how the mass is distributed. So let's just look at this. So a sphere, so just to kind of highlight these, the I for a sphere is 2/5 mr squared. The I for a hoop is mr squared. The I for a solid cylinder, we'll just put cylinder to keep it simple, is mr squared. Let's put the 1/2 in front to make it obvious. Which of these will rotate to the bottom the easiest? The one that has, given the same m and the same r, all of them have mr squared. So whatever those numbers, just call them 1. Make the mass 1, make the radius 1. Woo! They all have the same m, they all have the same r. So which will be the smallest? The sphere. It's really tempting to look at the cylinder, but let's just convert this cylinder to the same common denominator, and I'm going to commit, this may be a sin, I don't know, putting a decimal in a fraction. It's really tempting. It's really tempting to look at that sphere and say 2/5 is bigger than the half. Totally happens. But if you're careful, you realize 1/2 is 2.5 over 5. Very slightly bigger. Very slightly bigger. So that cylinder will reach the bottom soon after the sphere will. But it will be later. It is harder to spin a cylinder than it is a sphere, given the same mass and the radius. So, again, super interesting table, kind of describes to you. We even have a slab. That one's interesting. The reality is, if you have, let's just say you all have a tire. You could approximate a tire as a cylinder with some thickness, let's call that the rubber, and then you have the hub, and you can model that as a, do we have it up here? A very thin cylinder. A disc is a very thin cylinder. They're the same thing. That's kind of an interesting thing. If you all take a cylinder and you squish it, it's a disc. So this solid cylinder right here, see how it says or disc? Same thing. So sometimes when you're finding moment of inertia, you take an object and you break it into different pieces. Oh, it's a disc here, a cylinder here, a sphere here. That's one way. The reality is, what's more often that they're going to do? They're going to put this thing on something that spins, see how hard it is to spin, and just calculate the moment of inertia using just measurements. Because these things get really complicated really quick. And you can get a theoretical value of it, and computers can do that for you. Computers can do these these distributions no problem. But at the end of the day, if you really want to know what it is, just put it on something and see how hard it is to speed up. Give it a torque, measure the angular acceleration, do the math. Yeah.
So then, is air a big factor? Because I'm just thinking, okay, so then why aren't guns just solid spheres instead of, not guns, sorry, bullets?
Oh, that's aerodynamics.
Is it because
Yeah, that one's more of
even
aerodynamics.
though it's easier, it has more inertia, it's easier to.
Yeah, because you do want a bullet to spin. That we're going to learn that's conservation of angular momentum. So anything that spins, we want to keep spinning the same way. So maybe a bit more kosher to a football. People will spin a football because it keeps it stable. It keeps the, we're going to learn about that. Once you get something spinning, it doesn't want to tilt that axis of rotation. That's called conservation of angular momentum. That's one of the last things we cover. Once something is spinning, it wants to stay that way. If you try to rotate it, and there's all sorts of cool demos and examples of that, it'll actually kind of fight you. So if you throw a football to spin, keeps it stable, and that keeps the orientation of the football in the direction that's more aerodynamically favorable. If you want something to go in a straight path, make it spin. Baseballs are the same way. As far as what's the ideal shape, a more conical section is more aerodynamically favorable because you're not hitting as flat surfaces. The more smooth that transition is, the easier the air slips around that object. Yeah, it's good questions. Okay, so great. Moment of inertia. You do not have to have these memorized. I want to make that very clear. Anytime I give you all an equation, I do not expect you to have it memorized. If you need to know these, I will give them to you. So for example, this problem here at the beginning, I would have given you the moment of inertias of these various objects. So if I asked this problem now after I taught you all stuff, I would have given you the moment of inertia and said which one will reach the bottom of the first. The smaller the moment of inertia, the faster it's going to reach the bottom. What I do need you to know is this following slide. So remember, the axis of rotation matters. There's a really cool theorem, and to be honest, I don't exactly know the proof for it. I should probably look it up. I don't exactly know the proof for it. I probably should look it up, but if you say we have this sphere and it's rotating through the center, and I say that's boring. I don't want to make it rotate through the center. I want to make it rotate on the side for reasons. What's really cool, you don't need to do an integral. You do not need to do a whole new integral. It's really simple. You take the original moment of inertia. So for a sphere, the original moment of inertia is 2/5 mr squared. And what do you do with it? It's really simple. However much you shift it, you just add md squared to it. That's it. You just take the original moment of inertia. So here I have a cylinder. The moment of inertia for a cylinder is going to be, I don't have this memorized, so give me a second to find this real quick, mr squared. mr squared. Is that right? That seems wrong. 1/2? 1/2. 1/2 mr squared. This is the moment of inertia for a cylinder rotating about an axis. Hey, I want to rotate it. And you know what? Let's rotate it somewhere a little bit more convenient. Let's move it here. Let's move that moment of inertia that far away. Move all my pretty pictures over. There we go. Now it's pretty again. So I took that moment of inertia and I took that object and instead of rotating through the center, so here's my cylinder is rotating through the center. Now I'm going to rotate it around the outside, which is very awkward, but it's now kind of rolling around this new dotted line, this red dotted line. Boop. So that's my new axis of rotation. What's my new moment of inertia? Super simple. How much did I move it? R. So what's my new moment of inertia? I take my original, which is going to be 1/2 mr squared, and I just add the mass that the object has, easy, however far I shifted it. How far did I shifted it? Shifted it. How far did I shift it? R. What's my new moment of inertia? Do I want to, I'll leave it as a fraction. You know what? I will put it as a decimal. Traditionally, we put it as a fraction, but who cares? It's easier to understand this. What's 1/2 plus 1? 1.5. Boom. New moment of inertia. Done. Easy. No calculus. No triple integral. So it's really cool. And this is true of anywhere. I can move this thing super far away, and I just add mass times however far away I shifted it squared. It's so simple. It's really cool that it works out that nicely. So, if you have a wheel spinning and you have like a sphere stuck to that wheel somewhere, you're like, oh, what's the moment of inertia of that sphere? Just take how far away it shifted and add that, and boom. You can calculate the moment of inertia of that object. So what's cool is, I mentioned a ball bearing to you all. Really super common device. Anything that rotates has one of these things in it. It's a sleeve with some ball bearings inside it. So this could be modeled as two cylinders, an inner cylinder and an outer cylinder that have no thickness to them, and a bunch of spheres all rotating about the spot. And you could just figure out the moment of inertia of the outside cylinder, the inside cylinder, and then a bunch of spheres whose axis of rotation is shifted by some distance. Add it all up, boom, you got the moment of inertia of a ball bearing. Or I think it's called, the ball bearing is the thing inside it. Gosh. What's this thing called, y'all? It's the thing that makes us spin. It's got a ball bearing in it. The ball bearings are the spheres.
It's also called a ball bearing.
The whole thing called a ball bearing too? Oh, that's terrible. Alright. Isn't the things inside it also called ball bearings? Oh my gosh, I hate that. Yeah, a bearing. Maybe just don't put the word ball. They still call it, yeah. Either way, you can do it, even though it seems really complex, you can find the moment of inertia of that pretty accurately, theoretically. Yeah.
So this moment of inertia that you've moved over, would that point on the outside of the cylinders be touching it constantly?
Yes. Yeah. That axis. So the question was, this new axis of rotation, is that always touching it? Yes. So this cylinder is revolving around it. So it's going to go woo and kind of three-dimensionally go around that. That's awful. But that's the idea. Yeah, it would swivel around it. All right, so let's end class. This will be kind of our last one, parallel axis theorem. In the next class, I'll do some math. A sphere has a moment of inertia of 2/5 mr squared when spun through the center. See, I told you, I'd tell you these equations. Like, you don't need to have any of these memorized. If we instead spin it around an axis tangent to the surface, like the last one, I shift it over, what is the new moment of inertia? So I took my axis of rotation, I shifted it over. I'm going to let you all determine how much it gets shifted over. And so you go, you know what, I will be so kind, and I'll even put the parallel axis theorem, because it's going to be on your equation sheet. So the new moment of inertia is the original plus the mass of the object times however far you shifted it squared. There you go, that's the equation for it. So you just need to apply it to this situation. And this is true of any object. It doesn't matter how crazy that object looks. Take a piece of Play-Doh and shift the axis of rotation and this works. Again, I should really look up the derivation for this whole parallel axis theorem. I have the sinking feeling it's going to be really complicated, but anytime there's a simple relationship like this, you got a 50-50 shot of the derivation being simple or absolutely awful. It's funny how that works. All right, so we'll go to 135. The math here is pretty simple. I keep saying that, but any clicker question, I purposely make the math simple. All right, 5, 4, 3, 2, 1. All right, so we just plug in the things. So it's 5/2. Nope, 2/5. 2/5 mr squared plus how much did I shift it? I shifted it by the radius. You add those together, y'all. Let's make some least common denominators. It's good for us. 5/5 mr squared equals 7/5 mr squared. This is the type of problem I could totally ask you on a test kind of thing, because there's no calculus here. This is something you all can do. It's a clicker question. Boom. Great job. You all did it. Next class, we'll do some math. and integrals, and it'll be good. So much fun. Have a great day, y'all. See you Wednesday.